Yes, hello everyone. And yeah, I'm going to be talking today about long frames and INP, understanding the post-load performance. My name is Vinicius Dallacqua, and I am a lead engineer at Gideon. Originally from Brazil, worked in many places, Klarna, Spotify, to name a few. And I have been working with performance for right about 7 years now, and I think that for everyone that's here, we are all somewhat familiar, at least some form of performance tooling, and we are also somewhat familiar with maybe one or more performance metrics. Hopefully, most of them. But most of times when we talk about performance, we are biased towards load time, and it has been like this for a long time now. We focus on delivering a good loading experience, and there is a reason for that. An app that or a website that loads slow, it can lead to frustrating experiences and high bounce rates for your clients or your own websites. But it can also happen that when we somewhat forget the post-load part, we are introducing those same frustrations to our websites because that's where most of our users will spend most of their time. For a long time, even responsiveness terms being thrown around for metrics and measurements was somewhat bound to load time metrics. How long does it take to be interactive? How long it takes for the browser to respond to the first user input? How long did the JS parsing and loading block the main thread? All of that focuses on the loading experience. That's why we now, well, for a while now, have INP on the metric side and LOAF on the API side to help us better understand and improve interactiveness. But I'm getting a little bit ahead of myself on this. In order to truly appreciate INP and LOAF, we need to get a bit of history lesson on how our performance metrics got here and why they evolved the way they did. You can only connect the dots looking backwards. A little bit of context can give great perspective on the reasons why we use metrics that and apply techniques the way we do nowadays. So let's take a look at those early days and see how the landscape looked like. We're going to take a look at the rail model. We're going to take a look at early days of interactivity metrics and INP and LOAF later, see what led us to those. And we're going to see initially tools like rail model, for instance, and how they shaped the perspective of how we treat performance nowadays. So let's first take a look at the rail model. Introduced in 2015, it stands for response animation idle and load. And it was a significant step forward on how we think about our users' perception of interactions. Each part of the rail model came with a set of recommendations that served as a mental framework to build responsive websites. But let's focus on the response part. It stands for responsiveness, not HTTP response, and it started making more popular a set of timings and for referencing on how to think and how to should you organize the work you do with your JavaScript around user inputs. It made popular a set of timings to help us use as a budget when thinking about task execution times. The 100 millisecond window was the total amount of time to process user input. And that's including queuing the input and event handlers and handling any possible dispatch of event handlers and listeners and tasks that generated after that. So taking consideration that, tasks were left with a 50 millisecond budget to execute and yield to the main thread for the browser to ship a new frame and serve a 60 frames per second experience. Any tasks that exceeds this budget may incur visual jank and or delay a visual update to the user, which leads us to the early days of performance and metrics and tooling. Although those metrics were almost entirely focused or somewhat biased towards the loading experience, it was a great starting point. With metrics such as FCP, FMP, and LCP to measure visual completeness, and metrics that gravitated around CPU idleness after load, such as first interactive and first consistently interactive, which later got named to first CPU idle and TTI. But we lacked a good way to measure and understand performance problems around user interactions. Our first metrics to assess interactivity still measured around events that happened during or right after the page load time, assessing how much time it took for the browser to download and parse assets and be able to respond to the first user inputs. Metrics such as TTI that try to assess precisely that, and also FID that assess how much delay it was incurred for the first user input. There's also the total blocking time, and though it's considered a lab metric, and lab tools primarily assessed it in correlation to TTI, it was a step into the right direction on trying to create a metric around the impact of long tasks on the page's responsiveness. So now let's take a closer look at how those metrics were computed and understand some of their shortcomings. And here we see a good reason for that. So not sure how many of you have seen this graph before. Let's take a closer look into TTI. First, conceived as first consistently interactive, it tried, or still tries, TTI got removed actually, well, will be removed. It tries to assess when the browser is able to respond to interactions reliably. I think that the original name conveys the meaning of the metric quite well, but it doesn't have a catchy acronym. So the graphs taken from on this image, it's from the original Google Docs study for the metric, showcasing the series of events that the browser would account in order to be able to compute TTI. It showcases how confusing the metric is to compute, how complex it is to even talk about the different nuances of every single thing in that graph. So it's one of the reasons why TTI kind of fell out of fashion, because it doesn't really help you all that much, and also can be a little bit biased towards serving different assets. So now, using the official chart taken from the web.dev, sorry, for FID, we can see how TTI and FID are connected, where TTI measures the total time for the browser to be able to start responding to interactions reliably, and FID measures the very first interaction for any delay and in handling the user's input. FID was a good start, an attempt to assess disruption and jank on serving the first interaction, giving us a number in milliseconds for how much time that interaction response got delayed. With the metric also came some recommendations on how can we defer script execution to avoid slow interactions happening around the load time and other problems related to interactivity around the load times and right after load time. So now let's take a closer look at total blocking time, TBT. As a lab metric, it helped us understand and measure the total impact of long tasks. The metric is not necessarily connected to user interactions, but instead how much work is being done on the main thread, and which can impact user interactions and visual updates. This metric was used by lab tools such as Lighthouse to measure impact of long tasks during load time. It's not necessarily a load time metric though, but instead a measurement of long tasks blocking the main thread over a certain period of time. Since the rail model inception, we try to understand the impact of a busy main thread on our users' experience with fancy acronyms and mental models to help us divide work and better understand the impact of long tasks when we try to keep a responsive and delightful user experience as the key result. Speaking of long tasks, the long task API is another important milestone. If total blocking time is the total blocking time over a period of time, the long task API provides granular access to all the long tasks that happened over such period of time, giving us some form of enumeration and basic attribution model over those entries. Although that was a great step forward, it did not really solve our problems. The basic attribution model gives us more granularity over and some information over each long task, but it fails to give us proper insights over which script or function it might be attributed to, giving us not much more than a timestamp and a blocking duration. This quote that you see on the slide actually comes from the LOAF article about shortcomings of the long task API. Another important point is that if you only consider long tasks as a source of interactivity problems, you're eliminating an entire class of performance problems that has to do with styling and layout that can also prevent the browser from responding to interactions and slow down production of new frames. So with that knowledge, the Chrome team started investigating how could they create a better, more user-centric responsiveness metric. One that can observe not only the load time, but post-load time part of the user experience, and also encompasses all parts that might be causing slow interactions. This image was taken from the Towards a Better Responsiveness metrics in article that preceded the announcement of INP. And you can already see in that image a lot of resemblance of how INP as a metric functions and identify its different parts. You can see also you can see in there the delay section, you can see the processing time section, and you can see the shipping of the next frame being shipped to the user as a full account of the interaction duration. This is also very well represented on DevTools nowadays. On the interactions track, on the performance panel, we can visualize the input delay and presentation delay being represented as those whiskers on each end of an interaction, and the processing time as the solid bar. Those parts combined, they represent the totality of an interaction duration with all of the tasks and call frames displayed on the main track, the main thread track below. Which now gets us back to INP and LOAF. So let's start with INP. INP as a core web vital tries to assess the page overall responsiveness by giving a score based on the longest interaction observed. INP, similarly to CLS, is a session-wide metric, and it replaced FIT as a core web vital as of March 2024. It's important to note that not to penalize highly interactive websites and applications, the highest interaction over every 50th interaction over the session duration will be dropped. This is to make sure not to account for random hiccups and provide a better baseline value for the metrics score. In this image, we have a really good visualization of the INP metric and its different sections. It comes from the INP article itself on web.dev and showcases what is considered an interaction and all of the different parts for the INP score. Every part of an interaction duration can be accounted for the attribution model for the score, which brings us to low F. It introduced us to a concept of an animation frame, which, similar to the INP metric, shifts our perception of how we section portions of work on the main thread. We can use the same model from the INP article to understand what an animation frame is and its different parts. And same as INP, it goes from solely focusing on the JavaScript part to focusing on all of the work needed to ship a frame, from any delay in execution caused by a previous task or the task executed during the animation frame to any delay caused by styling and layout. This helps us better understand any problem that might lead to slow interactions or jank, and it focuses on how the user perceives the performance, connecting visual updates and responsiveness to a single attribution model. It's also important to note that long frames can happen at any point in time, as script execution can come from many different sources and trigger different side effects, including visual updates with or without direct user input. So animation frames are a really useful tool to identify all sorts of different problems connected to responsiveness, which means that the LOAF API and animation frames as a unit of work is a much better attribution model to work with. It provides a much richer data as an attribution model as well. Similar to the long task API, we have a timestamp and a duration, but also we get a breakdown of all the segments of the animation frame as a unit of work. So this slide, it introduces the different data points that you have from the attribution data on the LOAF API as you get an entry from the observer. So all of this data is within the LOAF article, but here you can see the different parts. With the data provided by the animation frame entry, we can section all the units of work that happened during the interval of the animation frame, and we better understand where the animation frame spent most of its time on. So here you see on the slide how to calculate the different portions of work based on the different data points from the entry on the LOAF API. It also provides better attribution when it comes to any possible scripts that could have resulted on a long execution time, giving separate timings per source and details such as which script and function caused it. So it solves the problem of the attribution model when it comes to identifying precisely where the biggest part of work came from. So it's not just understanding which part of the work is the longest, but also where does it come from, which script and which function. And here's a quick example of how attribution data looks like if put it all together, coming from the animation frame entry. This is just an example data pulled. So going to the next. It's important to note that the INP entry might have more than one LOAF entry, since the input delay attribution model coming from the LOAF would be also connected to its own LOAF entry. So you can have, since the INP can also have delays on each end, especially coming from an input delay, the input delay can come from another animation frame. So it can belong to more than one, the INP can have more than one entry in that case. It's also important to remember that each LOAF entry might have multiple scripts attributed to its execution time. So when it comes to visualizing INP out in the wild, nowadays we have the dev tools with the insights is a great place that anyone can go to. We also have two examples from third parties. One here is the Vercel toolbar, which is part of the hosting service on dev mode, I believe. And you also have on the right a tool of my own making called PerfLab. And I am basically using the DevTools performance panel as a component to extract data out of traces and generate report cards, which you can see have every single basic understanding of the trace within the trace panel and the data from the trace underneath. And you can see the INP entry being highlighted with the overlay. There's another trace visualized, showcasing an animation frame. And so I'm zoomed in into an animation frame entry within a trace. And the LOAF entries are, so this shows that the LOAF entries may not be linked within an INP metric or an interaction itself. So you can see that this particular long animation frame is not linked to any interaction. But this could be a potential source of delay to an interaction or even jank on animations. This particular animation frame was part of a trace session where I was trying to analyze the loading experience of a page, trying to understand the visual jank around the experience that was happening precisely like right during the loading. There were some animations going on. And even though there was no direct user input, the page seemed unresponsive and turned out there was a lot of things going on the main thread, as you can see visualized from this particular section of the trace span. Made very nice to be identified with the annotations and overlays and insights that now we have on DevTools, which is a fantastic new addition. Not so new, but great addition. The LOAF API and animation frame form a great addition to our toolkits, but it's not free from shortcomings. So there are a few things that are important to make note of. An important one is that script attribution can only come from scripts running on the main thread of the page. That includes same origin iframes, as longer animation frames can be caused by third-party scripts executed on your site or even Chrome extensions. So the attribution model doesn't necessarily capture those. There are also problems as of time of the writing of those slides. I haven't checked back since, to be honest, but there were problems on attribution or source information with event handlers and callbacks and inline scripts with anonymous callbacks as well that could not be represented within the attribution models. And we have come very far since the early days of performance and metrics and tooling, and we have such incredible tools nowadays at our disposals to help us better understand and improve our experiences on the web. It's a truly, truly incredible journey since then. And INP and LOAF, they're fantastic tools that everyone now has access to. And I believe that they're really, really great to help us understand performance and interactivity in general, and help us ship a delightful user experience to our users. Well, thank you very much. And that is my Twitter X handle. And on the announcement, you've also had my Blue Sky handle. And thank you. That's about it for me.